Hello, good people. Today we are talking about Pascal's principle and pressure with depth in a fluid. These are two different topics. We'll start by addressing Pascal's principle, and then we'll talk about pressure with depth in a fluid. Let's start with Pascal's principle. Pascal's principle says that the pressure exerted on a contained fluid is transmitted undiminished throughout the fluid, acting in all directions and perpendicular to the container. This is a property for fluids. We're in our unit on fluids, and today we are talking a lot about fluids today. Here's Pascal's principle. If I were to take a solid, like this candle, for example, which happened to be sitting on my desk. If I were to take this candle, and I were to push right here on this corner of the candle, put a little bit of pressure here. When I put pressure on that corner of the candle, well, it's not as though the whole rest of the candle says, wow, we're all feeling the pressure. If I asked the candle, hey, where are you feeling pressure? The candle would say, I'm feeling pressure right there, like right in this general area, right where you're putting the pressure. It's not as though I put pressure here and the whole rest of the candle goes boop and kind of rises up because of the pressure that I put here. No. But what does happen is that if instead of a candle, I had a fluid, something like a liquid or a gas, because that's what fluids are. And if I were to take my finger and push down at the water in one place, that would push up on the water in the rest of the places, and the rest of the water would rise up. If you put pressure on a fluid in one place, that pressure gets exerted and is transmitted undiminished to all other parts of the fluid. So if you put pressure on some water in one place, that will put pressure on the rest of the water everywhere else. Let me kind of show you a little bit of an example here. The first example that we are going to look at is the concept of drinking from a straw. Now, most people, if I ask, how does a straw work? Most people they sit there, they think for a second, and then they say, I actually don't really totally know how a straw works. Because we just use these things in our daily lives, and we don't ever ask questions about okay, I know that I have a straw. I know that this is what I have to do to make this straw, bring the water up towards me. I know that that's how it works. But I don't actually know, I can't draw a good thing here. Oh gosh, browse with your voice. That sounds cool, and I'm not interested. Okay. Here's a cup. It's kind of a wide cup, but there you go. Let's draw some water in my cup. Oh gosh, this is just embarrassing. I should have pre-drawn cups. Pre-drawn cups are some of the best cups. Okay. There's some water in my cup, which I don't love because it's crossing over the lip of the cup, which just looks bad. It just all looks bad. Okay, water in my cup. Like this. Yes. You probably could have drawn 7 cups in the time that it took me to draw 1 cup. And then I'm going to draw a straw here. Boop, boop, doop, doo, doop, doo, 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 doo. Do, 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 do. That's a very wide straw. Okay, no, I'm leaving it. It's fine. It's not that big of a deal. Okay, here I have a cup of water with a straw in it. Now, most people, when I ask them, hey, how does a straw work? They actually don't really know the answer to this question. We just use things all the time. Hey, do you think that you put your mouth over a straw and you breathe in, and then all of a sudden the water says, I am being summoned upwards by the breath in, and so now I shall climb up the straw to rise up to the place, the source of this breathing in. No, that's not true. Otherwise, you could take just a cup of soup like this, and you could go, and you could suck up your soup without a straw or anything. No, there has to be something different about the straw, something that's making this situation different. You do not just suck water up into your mouth like magic. No, there has to be something that is pushing the water up the straw, some reason why that water is climbing up the straw. Well, here's the truth, is that as the water is sitting in this cup, it is actually under a great deal of pressure. The same way that you and I are under a great deal of pressure right now. It's under some air pressure. The atmosphere is pushing down on the top of the water like this. Well, when you are not using the straw, there's also atmosphere pushing down in the straw as well. And so you have a push down right here, a push down right here, a push down right here, a push down right here. Now, what happens is when you put your mouth over the straw and you suck in, what you're doing is you're taking away some of the atmospheric pressure that's over the straw here. So you just get rid of the atmospheric pressure sitting in the actual straw, like this. When you get rid of the atmospheric pressure in the straw, what happens is then the whole atmosphere is still pushing down on the outside. So the atmosphere is pushing down here, the atmosphere is pushing down here, the atmosphere is pushing down here. Well, Pascal's principle says if you push one place on a fluid, the whole fluid feels it. And so if you push down here, but now there's nothing pushing down here to keep this water stopped, to keep this water down, well, you push down here, that pushes down here, and that pushes down here, and then that pushes up here, and it pushes the water up the straw like this. Because you push down and the water levels raise up. It's not that you are somehow creating a magic force that allows the water to climb up the straw. That's not what happens. It's that the whole atmosphere is pushing down and pushing the water up the straw. If you've ever had a water bottle before that has a straw component to it, then you'll see that there has to be some sort of like hole in your lid or something that allows the air to get back in there. Because if you take the water off, if you take the atmospheric pressure out of the straw here, and then there's no way to replenish the atmospheric pressure here once it pushes it down, well, then you can take a sip, and then after you take a sip, you can't keep drinking anymore because you need atmospheric pressure here to push the water up the straw. And so that's why all of your little, like if you have a lid that has a straw in it, it has a little hole to allow the atmosphere to keep on going in there. So then it keeps allowing the atmosphere to keep pushing the water up the straw. That's the idea. If you put pressure at one part in a fluid, the whole fluid feels it. It's not like a solid where if I push down over here, nothing happens over here. If I push down over here, the whole fluid feels it, and it shoves the water up the straw. Another example is what we call a hydraulic lift. Let me show you what a hydraulic lift looks like. Actually, I'm going to draw it bold first, and then I'll annotate it with the little pen. Okay. Okay, there we go. Yay! This is a hydraulic lift. Guess what? It's hard to lift a car. If you wanted to lift a car, it'd probably be difficult to do. Why? Because cars weigh a lot, so it takes a lot of force. The force that it takes to lift something is as much as it weighs. Well, it sure does take a whole lot of force to lift a car since it weighs a whole lot. So lifting a car is hard, but we gotta do it sometimes. Like sometimes we gotta get underneath the car and we gotta be able to see what's going on inside the car. So we have to have ways to lift cars that are easier. This is why we use what we call a hydraulic lift. Here's what you do is you have basically one piston over here. You have this weird shaped container that's full of a liquid. Then you have this giant platform over here. And on this giant platform, you put the thing that's really heavy to lift, like a car. So the car sits over here on the platform. Doop, ba-doop, 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 ba-doop. There's my car. Thank you. Yes, I know I am very talented. I can't really tell which side's the front. I feel like this is the front of the car, and I feel like this is the trunk. Okay, so there's your car. It's sitting on top of this platform here, and this whole platform here, or this whole like box area thing here is filled with a fluid. Normally, it's not something like water. Normally, it's something like an oil or something like that. So this whole thing is filled with fluid. Now, here's what you do is you start by, you take this little piston here, and you apply some pressure this way. And here's the idea. If you apply some pressure this way on a fluid, then that pressure is going to push, 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 push. It's going to push all of the fluid, and it's going to push, 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 push. And then the fluid is going to push the car up like this. So you apply some pressure over here. Sorry, I want to draw that more clearly because you can't totally see it. You apply some pressure over here, and then that applies pressure to your car over here with the same amount of pressure that you pushed with. So if you push with some pressure over here, that same pressure is going to be transmitted undiminished to all parts of the fluid, which means the same amount of pressure is going to be transmitted over here. Now, here's where Pascal's principle is helpful to us, is because we say that the pressure that you apply on this side is going to equal the pressure that the fluid exerts on the platform that the car is on. Now, whoops, sorry, I moved my face out of the way. Now, the pressure that you put over here, that's the force that you apply over here divided by the area over here. Well, check it out. This is a little teeny tiny area. So that's a very, very small area. And so you apply a very, very small force. The force that you apply over the area that you apply it for, that's going to equal the force that the fluid exerts on the car divided by the area that it exerts it on the car. If you look at that area, well, in comparison to this teeny tiny area, that's a nice, very big area. So we got a big area over here. Which means you got something small divided by something small, that makes something medium. Over here you got something big. You need something big divided by something big to make something medium. And so you push with a little bit of force here, a little bit of force on a small area, that makes a medium-sized amount of pressure. That pressure transfers over here. You've got a big area, so it exerts a lot of force on that car, and it lifts the car up. Now, some of you are saying, wow, this hydraulic press, really, this hydraulic lift thing really does sound quite magical. You're telling me that you put in just a little bit of force and you get out a lot of bit of force? How is that even legal? Aren't we violating something like the law of conservation of energy or something? Like something has to be being violated here if you get to put in a little force and you get out a big force. Well, no. We are not violating the law of conservation of energy, and let me show you why. Basically, the volume of this fluid that you push down over here, that's going to be the volume that pushes up on the car over here. So what you're going to do is you're going to push down all the way to the bottom of this column here. So you're going to apply a little force. Whoa, that is not a good letter. Okay, you are going to apply a little force, and you are going to apply it over a big distance, delta x, all the way down to the bottom here. Meanwhile, by the time this volume of fluid gets over here, it's going to push up the car, but it's going to push up the car just a little bit. It'll probably push it up about this much or so. And so over here, it pushes with a much bigger force, but it goes a much smaller distance. And so we got a whole simple machines kind of situation again, where you trade force for distance. You put in a little bit of force, and it goes a much bigger, but you go a much bigger distance to get out a big force with a much smaller distance. And so the law of conservation of energy is still upheld. The amount of work that you put in is still the amount of work that you get out. This is the idea of Pascal's principle. You put pressure one place on a fluid, and that pressure goes everywhere else in the fluid, and then that pressure can push on the walls of its container. You see here, it's pushing on the wall of its container here. If I were to take like a water balloon full of water, because that's what you would fill a water balloon with, and if I were to push on it one place, then it would push on the whole balloon everywhere. It would push on the walls of its container, and it would push perpendicular to the container. So if there's a wall like this, then the fluid is going to push this way onto the wall. It's not going to push up along the wall like that. That doesn't really make much sense. So that is the main idea of Pascal's principle. Now that we've covered Pascal's principle, we are going to talk about a totally separate topic, and that topic is going to be pressure with depth in a fluid. These two topics, I like to think of them as completely unrelated and separate ideas, and I think that's helpful to students too. The reason why we talk about both of them on the same day is because they both have to do with pressure, and they are deep down related to each other, and we can talk about how they're related. But I found that if I say, like, I guess these two things are the same, then students are, or these two things are related, then, and I emphasize the relatedness, then students start to get them confused, because they both have to do with pressure, and they both have to do with fluids, and students say, wow, that was a lot of pressure and fluids. I'm pretty sure you're saying the same thing twice, and it's not the same thing. So this is a totally different thing. I like to think about it as a totally different topic. So we are going to transition now from one topic, which is Pascal's principle. Yay, fun topic. And now we're going to transition to a totally different topic, which is pressure with depth in a fluid. Let's go. Let's do it. Here we go. A brand new topic for us requires a brand new blank canvas page. Today I was thinking about how many canvas pages I've made before, because I probably make a few every video, and so that has got to be, like, if we really scroll down here, we would probably see a lot of pages. Okay, new drawing. Let's do it. Okay, here we go. This is our second topic of the day, which is pressure with depth. Here's what we're talking about when we're talking about pressure with depth. You go to the bottom of a swimming pool, and there is a whole lot of pressure. Way more pressure than when you're at the top of the swimming pool. And that's the idea of pressure with depth. The deeper you go in a fluid, the more pressure that you experience. So as you're deeper and deeper and deeper in the swimming pool, or deeper and deeper and deeper in the ocean, then you get more and more and more and more pressure as you get deeper and deeper and deeper. And we're going to explain why that's true. Notice the difference between pressure with depth and Pascal's principle. Pascal's principle is for like if I had some fluid in a container, there's the bell. If I had some fluid in a container, it's for contained fluids. Like if I have that fluid in the hydraulic lift, or if I have like water contained inside of a cup with a little straw. Like it's all things that are contained, and you push down on one part and then it pushes on the other part. So this is like the pressure, or Pascal's principle says you push at one part of a fluid in a container and that pushes on the fluid in another place in the fluid in the container. That's Pascal's principle. Pressure with depth is not the same thing. Pressure with depth says as you go deeper and deeper and deeper in the ocean, it gets more pressureful. Notice this is not like someone coming along and putting their hand on the ocean and pushing down on the ocean and another part of the ocean raises up. That's not what we're talking about. We're talking about if you're getting deeper and deeper and deeper in the ocean, you get more and more pressure. Okay, let's take a look at a really actually very lovely derivation. Suppose that you go up to a water fountain. I nearly nailed it. I was so close. Close enough that it just might work. Okay, suppose that you go up to a water fountain here. I'm not talking one of those water fountains like the ones at school where you fill up your water bottle. I'm talking about a magical wishing fountain where you can go, and it probably has some like statues in the middle, like maybe some dolphins that are squirting water out of their mouths or something like that. And you can go and you can throw in coins to have your wishes granted. Now suppose that you walk up to this water fountain, suppose that it is filled to the brim with water, and you take your favorite lucky penny and you toss it into the fountain and you make a wish, and the penny you watch as it lands right there down at the bottom of the fountain, and it lands, oh gosh, those eyes are way too close together. It lands, boop, heads up for good luck. And so you see that little penny. That's a terrible, I'm so sorry, I have to fix it. It's kind of goofy looking, and so maybe I should have kept it, honestly. Okay, that's pretty good. That's pretty adorable. Okay, you watch as your penny lands face up on the bottom of the fountain. Now, that penny is sitting at the bottom of the fountain, and sitting at the bottom of the fountain, it is experiencing a good deal of pressure. Not just because granting wishes is a very pressureful endeavor, although that is most certainly true. Any penny will tell you that puts a lot of pressure on a penny when you put all your hopes and dreams on that one little penny. But it's also experiencing pressure because it's under the water. Suppose that it is under the water, and suppose that the height of the water in the fountain is a height h, like this. The water, or you could say that the water is like depth of h. So what we're looking at here is, you would say this penny is under a lot of pressure because it has the whole weight of this column of water that is now sitting on top of that penny like this. And the whole weight of this column of water is pressing down on the penny and creating some pressure. We would say, this is a lovely derivation, you're just going to love it, that the pressure that the penny is experiencing is equal to the weight of the water that's sitting on top of the penny divided by the area of the penny's face, because that is the pressure that that is the area that the pressure is getting exerted over, is the area of the penny's face. So it has the weight of all of this water on top of it divided by its area, and that's the pressure that the penny is experiencing, not including the pressure from your hopes and dreams. Now, if we wanted to say, how much is this pressure that the penny is experiencing here at the bottom of the fountain? Well, first, let's start with this. We would need to find the weight of the water sitting on top of the penny. Now, I didn't give you actually like anything that would be helpful here, like the mass of the water sitting on top of the penny. That would be helpful because we could use Fg is equal to mg, where m would be the mass of the water sitting on top of the penny, and g is the acceleration due to gravity, classic. So we could use Fg is equal to mg to calculate the weight of the water sitting on top of the penny, except that I didn't give you m. Now, yesterday, or in the last video, or the last time we talked together, we found a way to calculate the weight of some water using the concept of density. Look back in your notes and check. What was our strategy? How did we do it? How did we get this thing done? Well, you said, okay, we use the concept of density. Density is mass per volume. So we say if we want to know the mass of the water, we could just do the density of water, which we know deep down in our hearts, times the volume of the water that's sitting on top of the penny. I could then take the mass of the water, which is the density of the water times the volume of the water. I could plug this back in here, and I would get that the weight of the water is equal to the density of the water times the volume of the water times G, like this. Then I could plug in for the volume of the water a formula for the volume of this cylinder of water that is sitting on top of the penny. And the amount of water that would be sitting on top of the penny, the volume of the water sitting on top of the penny here, would be the volume of a cylinder. And you know that the volume of a cylinder is the area of the base of the cylinder times the height of the cylinder times G. Now, we could take this and we could plug this back into our pressure equation here. And here's what we would get. We get that the pressure that the penny is experiencing is equal to the density of the water times the area of the base of the vertical column of water sitting on top of the penny times the height of the vertical column of water sitting on top of the penny times G, all divided by the area of the penny. But now, take a look. Isn't the area of the base of this column of water that is sitting on top of the penny, isn't that the area of the penny? Like, isn't the area of the base here also the area of the penny? So these two would cancel out, and you would be left with an equation for pressure that looks like this. We would say that the pressure that the penny is experiencing is equal to rho G H. And this is our equation for pressure with depth in a fluid. This is what we call gauge pressure. And it is the pressure from being at a certain depth in a fluid. That's what gauge pressure is. It's the pressure from being at a certain depth within a fluid. As you add this to your bag of tricks, can you just make a quick note to yourself? What factors does gauge pressure depend on? What factors does gauge pressure depend on? You're saying, okay, Miss Wilson, well, it looks like it does depend on the density of the fluid that we're in. Yes, that's true. The pressure that anything experiences when it's a certain depth under a fluid depends on the density of the fluid that's sitting on top of it. If you have a more dense fluid sitting on top of you, then you would experience more pressure than if you had a less dense fluid sitting on top of you. The other thing that it does depend on is G, the acceleration due to gravity. And the last thing that it does depend on is the height of the fluid above you, which also means it depends on how deep down you are. The deeper down you are, the more the height of the fluid above you, and the more pressure that you experience. Notice, does it depend at all on the penny? No, there's nothing in this equation that is like from the penny at all. There's only the density of the water, the height of or the depth that the penny is at, but it doesn't depend at all on the actual penny itself, which means that any object placed at this depth would experience this pressure. We would say that that pressure is there regardless of whether or not something is there to feel it. A little water molecule sitting at the bottom of this water fountain would experience this pressure. So there is always this pressure here regardless of whether or not anybody's there to feel it. Notice it also doesn't depend on the volume of the fountain. If the fountain was a little bit bigger, like if it was a little bit of a wider fountain, that wouldn't really matter. But what would matter is if it was a deeper fountain and you were at the bottom of a deeper fountain. But the volume of the fountain doesn't really matter at all. Okay, now here's the thing. This penny is under a great deal of pressure from the water, but it turns out that that's actually not all of the pressure that the penny is experiencing. The penny is experiencing additional pressure as well, because on top of the penny and on top of the water, the whole atmosphere is pressing down. And so the atmosphere is pressing down on the water, and that makes the water press down even harder on the penny. So if you wanted to talk about the total pressure that the penny is experiencing, once again excluding the pressure of your hopes and dreams, the total pressure that the penny is experiencing, that's not just the gauge pressure, it's the atmospheric pressure and the gauge pressure, because the atmospheric pressure adds additional pressure to the pressure that the penny is experiencing. So we say that the total pressure that anything is experiencing when it's at a certain depth in a fluid is equal to the pressure of the atmosphere plus the gauge pressure, which is rho GH. And you can start with either one of these as an original equation. Oh, I don't like that I just cut into my fountain. Let's not do that. Ah, yes, narrowly missed. Okay. Gosh, I just need to give up on like putting this in a really fancy box and be like, it's okay, you don't need to double side all your lines. One side on all the lines was literally totally fine. No one was complaining. No one was sad. No one was like, can you please put an extra side on your lines? No, no one cared. Okay, here we go. So this is your total pressure, is the atmospheric pressure and the gauge pressure. Let's take or actually before we look at a quick example, as you add this to your bag of tricks, can you please make a quick note to yourself? Which would experience more pressure, or which would be a more pressureful situation? Sitting at the bottom of a 10-foot deep pool in Phoenix, Arizona, or sitting at the bottom of a 10 feet deep pool at the base of Mount Blue Sky in Colorado. Hey, you should be saying right now that you would be experiencing more pressure at the bottom of a pool in Arizona than at the bottom of the pool in Colorado at the base of Mount Blue Sky. Why? Because the total pressure that you would experience would be the gauge pressure, which that would be the same for each pool, but you would experience different atmospheric pressures depending on whether you're in Arizona or whether you're at the base of Mount Blue Sky in Colorado. If you're in Arizona, the atmospheric pressure would be greater than if you were at the base of Mount Evans. Hey, by the way, you can think about the whole atmosphere as being a pressure with depth problem. The deeper and deeper and deeper you get in the atmosphere, the more and more pressure you experience. As you get less and less deep in the atmosphere, as you go up in elevation, you experience less and less pressure because you are less and less deep inside the fluid that is the atmosphere. So Mount Blue Sky, the atmospheric pressure at Mount Blue Sky is less because it's at a higher elevation, so it's less deep in the atmosphere, versus at Phoenix, Arizona, you're a little bit deeper down in the atmosphere, so you got a little bit more weight of the air on top of you because you have to hold up all of the air on top. And so then you would experience more pressure down there than you would up here. When we're talking about pressure, a nice way to think about it is always, how much does this water have to hold up? The water at the bottom of the fountain, or the penny at the bottom of the fountain, that has to hold up all of the water above it. Water right here would have to hold up all of the water above it. Water right here would have to hold up all the water above it. Water right here doesn't have to hold up many water above it. So the pressure here would be the least, the pressure down at the bottom would be the greatest. And that's how pressure with depth works. Let's go ahead and try a pressure with depth practice problem. Bum, 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 bum. Oh, let's change our color here to light blue. Okay, here's a pressure with depth practice problem. Suppose that for your 17th birthday, your parents decide to buy you a submarine because they love you. Of course, I made a yellow submarine in honor of the Beatles. Huzzah. This is not a very good submarine. I've drawn better submarines in my life. Not like much better submarines, but like slightly better submarines. Okay, here's my submarine. It's got little windows on it, which is perfect because you want to look out at all the fish. And it's got one of these thingies too, which all submarines have. And that's how you know it's a submarine. Okay. Now let's suppose that you take your submarine out to play in the ocean. Which I don't know how you did that since you live in Colorado, but suppose that you did it. You go out to play in the ocean. And suppose that you dive in your yellow submarine down to a depth of, let's say that you go down to a depth of 700 meters so that you can see the fish. Now, you know that the radius of your submarine windows is equal to 0.25 meters. That's a pretty good size window. That means that the diameter of your window is about half a meter. So that's a pretty good size if you're trying to look out and look at fish. That's a totally appropriate size for your window. Here's a question. How much force would your window have to be able to withstand at this depth? Okay, well, here's what I'm thinking. I'm thinking the reason why it's experiencing a force at all is because it's under the pressure of all of that water that's on top of it. So I know that pressure is equal to force over area. The force that my window is experiencing is the pressure that it is experiencing because it's under the water times the area of the window. Now, when we're talking about the pressure that your window is experiencing or how much force it has to be able to withstand, do we care about the gauge pressure or the total pressure? The total pressure. Because we care about the pressure from the water, but the water is also being pushed on by the atmosphere. And so our total pressure would be the atmospheric pressure plus the gauge pressure, which is rho GH, times the area of the window. Now, you were given the radius of the window, not the area of the window. We know that this here is our radius r, so instead you're going to have to put in here a little formula for the area of a window, but luckily you know the area of a circle is pi r squared. So you say no problem. And now we are ready to go. We are ready to plug in numbers. The atmospheric pressure is a number that I would probably give to you, not one that you have to have memorized. It's 1.013 times 10 to the 5th pascals if you're at sea level, which you probably are, given the fact that you are in the ocean. Plus the density of water. This is a number that you have to have memorized. Very, very tricky number here. It's 1,000 kilograms per meter cubed. 9.81. If you don't have that memorized at this point, then that is insane of you. You would have to try really hard to not memorize 9.81 meters per second squared at this point. And then finally the depth, oh gosh, I'm going to run out of space. This is going to be so awkward, is 700 meters. Boop. Keep my sig figs clean there. And then I'm going to multiply, pretend that I multiplied up here, but I did bad, times pi times my r, which is 0.25. Actually, I'm giving us 3 sig figs. Sorry, team, to just switch that up on you all of a sudden. That's probably not good physics. Okay, now, if you plug this into your calculator, which you most definitely should do, then you would get that your windows would have to experience a force at this depth of 1.37 times 10 to the 6th newtons. That is 1,370,000 newtons. That is quite a few newtons for your window to experience. Oh gosh, I just am really bad at drawing lines sometimes. Oh, that was even worse. What? I need to come up with a new strategy for, except that one was beautiful. I really liked that one. That one was great. Okay, and there's your final answer. And that is all for today, folks. Today we talked about 2 different topics. We talked about Pascal's principle. That is what happens when you have a fluid in a container. You apply pressure to one place and that pressure goes everywhere else. So if you push down in one place, it'll push the rest of the fluid up because pressure in one place gets transmitted to the rest of the fluid. Then we talked about a completely different topic, which is pressure with depth, which says that the deeper and deeper and deeper you go, the more and more pressure that you experience. As each little spot that you're at, you have to be holding up the whole weight of all of the water above you. And so the more weight you experience, the deeper you go. So the more pressure you experience, the deeper you go. And we also talked about the difference between atmospheric pressure and gauge pressure. And that is all for today, folks. To end, of course, I am going to leave you with just a small reminder of how this all really does connect back to your childhood. When your mom would tuck you into bed at night and she would sing you sweet songs as you fell asleep. And you remember when she would sing to you, row, 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 GH, pressure with depth in a fluid. Find the force on a submarine. I betcha you could do it. So there's a little throwback from your childhood. I hope you have a wonderful rest of your day. Bye, good people. We'll see you next time.